Okay, let's start. So today we'll basically be done with chapter 15. This is the last part on angular momentum and conservation of. Okay, so that's the coordinate axis, and there's a particle which has a velocity v, and it's at a distance r from the origin. Then the angular momentum, which is h, about point O, is r cross with mass times velocity. Okay, so just like the moment, your moment is always defined about a point. Similarly, the angular momentum for a particle is defined about a point, and it is a vector, right? Because it's a cross product. So the other thing is relation between moment of a force. Okay, this is m or r cross f. We've done that before, and angular momentum. So we've seen that the moment about point O, so again O is the same point as shown there, is equal to r cross with f, where f is the external force on the particle. So f is the external force. Right? So that's going to be sum, because there could be multiple forces, F1, F2, and so on. But F is, so by Newton's law, F is mass times acceleration, or in other words, mass times velocity dot, right? Rate of change of velocity is acceleration. So then we can shove in f in the equation to get moment about point O is r crossed with OF, which is the same as r crossed with mv dot. Okay, but r cross mv dot is, if you observe this expression here, it's simply the rate of change of angular momentum, which means that this is equal to ho dot, right? So this formula says that rate of change of angular momentum, h dot, is equal to the sum of all external moments acting about the point O. Okay, so that's one thing. The other thing I want to talk about before I start solving problems is the principle of angular impulse and momentum. Principle of angular impulse and momentum. Okay, we just wrote MO equals H dot about point O, which is the same as THO dt. So what we can do is move things around, move the dt around to get MO dt equals THO, and the goal is to basically integrate that equation from T1 all the way to T2 . So this gives MO dt equals HO2 minus HO1. Okay. The thing on the right hand side is the change in angular momentum. So this is when the application of a moment will produce change in either angular velocity or linear velocity. So one is that instant when the moment is the time instant 1, and then time 2 is the other instant where you are trying to see what the effect of that moment would be. This is exactly like how we did the principle of linear momentum and impulse. Remember, integral f dt was rate of change of linear momentum. So I'm going to rewrite this in a slightly different way so that we can then start using that when we solve problems. HO1 plus T1 T2 summation MO dt is equal to HO2. Okay, so this is the principle of angular momentum and angular impulse and momentum. Okay, it says that h0 is the initial angular momentum of the system. Then the system is acted upon by a moment mo. Then the sum of that plus the integral mo dt will tell you the final momentum or angular momentum at a different instant of time 2. So sometimes you're given the moment. For example, you might be given moment is 3t or 3t square or whatever, and then you can integrate it. Sometimes you're not given the moment directly, but you're given the force, and you're supposed to find the moment from the force and then integrate. What I mean by that is, other way to do this is, you can write MO dt as R cross F dt. So if you're given MO, go ahead, put it in and take the integral. But if you're given F and not MO directly, then you first have to find MO using R cross F and then take the integral. Okay, and the final thing is conservation of angular momentum. So when the external impulse or external angular impulse is 0, or when the impulse is internal to the system, then that particular impulse does not do any work, or it doesn't change anything. So that means that the angular momentum is conserved. HO1 is equal to HO2. Okay. Note that this is possible if you look at these two expressions. HO1 equals HO2 only when integral m0 dt is 0. Okay, so either there can be no work done, so no angular external force or external moment, then that HO will be equal to HO2. But sometimes what happens is this body, the M appears internally to the system. Okay, when it comes internally, it doesn't show up with an external moment or external force. In that case, angular momentum is conserved. Okay, so that's it. So when you see a problem here is, and you've identified that you got to use the conservation of momentum or the principle of linear angular impulse and momentum, then here's how you go about solving the problem. So first thing is choose a coordinate frame. Second thing is draw a free body diagram. And third thing is, first you want to search for the fact that if MO is 0, or there's no external force or external moment, then you can use conservation of angular momentum. So HO1 is HO2. Or if that's not true, then use the principle of angular impulse and momentum, which says that HO1 plus integral T1 all the way to T2 MO dt equals HO at time 2. Okay. So in general, first is to identify if it's a particle problem. Once you know it's a particle problem, think if things are moving in essentially at an angle to the application of force. Okay, if they're moving in a linear direction, then you don't have to use angular momentum or angular impulse. You just can deal with the problem with linear impulse and momentum. Okay, when things are going in circles or going in a direction to the force, then that's when you typically have to apply angular impulse and angular momentum. Okay, so let's do the problems. So a 4-pound ball B is traveling in a circle of radius 3 feet with a speed of 6 feet per second. So that's given. The initial R and initial velocity is given. If the attached cord is pulled down through the hole with a constant speed of 2 feet per second, determine the ball's speed at the instant R2 is 2 feet. How much work is done to pull the cord down, and neglect the friction inside the ball. Okay, so in this problem, the string is pulled down with a velocity of 2 feet per second. As a result, clearly the ball moves inwards. Okay, at some point the radius r is 2 feet. You're going to find the velocity when the radius is 2 feet. So when r 2 is 2 feet. V2 is unknown, and that's something got to find. Okay, so things are spinning in circles, and that's why you want to think about angular impulse and momentum. Now, in this case, would you apply the conservation of angular momentum, or you apply the principle of principle of angular impulse and angular momentum? The thing you have to think about is there a moment? If there's no moment, use conservation. Or if the moment is internal to the system, use conservation of. In this case, the external moment is 0. Okay? This string is pulled down, so there's a force along the string which is pulling it down, but it doesn't really create a moment which spins it in that direction, in the circular direction. Okay? So there's F because it's pulled down, but that F acts through the particle, through the center, through this. So it cannot torque the system or apply a moment. So the thing to use is conservation of angular momentum. Okay, the free body diagram, you don't need to draw it here, but it's always a good idea to draw. There's a force F. And then, I don't know, if you want, you can put a normal force, mg. But really, it doesn't really matter here because it acts normal to the system. We are interested in the motion in the horizontal plane. So the effect of mg and n is not really important for us. So h, let's call this O. Okay, so I wrote this h as a scalar and not a vector because I'm interested in h about the, let's call this the z-axis. This is h about the z-axis. So if you like, I can write this like this: h o about z1 is equal to h o about z2. Okay, so I'm interested in one. So h is a vector, which means it should have 3 numbers to it: hx, hy, and hz. Okay, well, in this case, I'm only interested in the angular momentum in the z direction. So h is along k. So why is it along k? Well, m r cross v, r1 cross vb1 equals m r2 cross vb2, right? Now r is in this direction, in the horizontal plane. V is tangential to the plane. So when you do r cross v, you get a vector which goes in the negative k direction. That's why h is only in the z direction. You don't have to write the vector if you realize that. So this thing is in the, yeah, it's in the minus k direction. Again, this is in the minus k direction. Again, you don't need to write it if you realize it's in the z direction. I'm just showing it to you how that's in the z direction. So mass cancels. R is 3 times velocity b is 6 equals, the new radius is 2 feet times velocity b2. This gives vb2 equals 9 feet per second. Okay, so that's the velocity in the tangential direction, but the actual velocity is velocity of ball to, this is in the tangential direction. So the actual velocity is, it's actually sum of two things. One is the velocity in the tangential direction, and it's also the velocity in the radial direction, because the string is pulled down with a velocity of 2 feet per second. Right? So the actual velocity is 2er plus 9e theta. I'll just write what e theta and er is. This is e theta, and this is er. Our convention is er is positive when it's outward, right? So let me just change it here. I think we should write it this way, just to be consistent. So then this is going to be negative 2er, right? Because it's being pulled inwards against er, in the direction opposite to er. So this should have been the answer, not the first one. Okay, and then the next question is find the work done in moving the ball from the first position to the second position. Okay, and this is where you could use the principle of work and energy. You know the work done in the system is to change the kinetic energy from its initial velocity of 6 feet per second to its final velocity, which I just computed. So using the principle of work and energy, we have T1 plus U12 equals T2. So initial energy is half, by the way, the initial velocity, this should be 2, VB2, so VB1 is simply 6 E, let's see, it's 6 along in the tangential direction, so 6 E theta. Okay, and the reason why it's only 6 E theta is because initially the rope is not being pulled at 2 feet per second. It only has that velocity. So the initial kinetic energy is half m times initial velocity, which is 6 squared, which is the squared, plus u, should be summation u12 equals the final kinetic energy. So mass times velocity. So you got to find the velocity, which is the magnitude of VB2. So that's got two components, 1, 2, and other 9. So it's going to be square root 2 square plus 9 square. That shouldn't be square root, it should be 2 square plus 9 square, because VB2 magnitude is what we're interested in, is 2 square plus 9 square. So this is going to be the square of this, so it's 2 square plus 9 square. So everything there except U12 is known, so U12 is the work done. What I get is 3.04 feet lb. By the way, mass is 4 lb. Okay, they're given as 4 lb. I think the book wants to make me think that that's going to be 4 lb feet, so 4 lb weight, so it's going to be 4 divided by 32.2. The 4 lb weight is the right way to say it, and not 4 lb. Okay, is that clear? So here you're seeing what you're seeing is interestingly is that we keep applying things which are not part of this section, right? We're trying to use principle of work energy to start, which was in the previous chapter. Okay. The other thing is you could have totally done this problem using F equals ma. In this case, you'll have to use the angular moment equation, not just F equals ma. But it becomes a bit harder because you'll have to find the forces which cause the change in well, not for the first part, but the first part, this is the only way to do it. But the second part, you could potentially find the force which does work, right? It's going to be tangential. Sorry, it's going to be radial, which pulls the string. Once you find the force, you can then integrate that with respect to the distance moved. And that is all going to be more complicated than actually using the principle of work and energy. So second part can be done a different way, but this is the easiest way to do it. Okay. Any questions? So two blocks A and B each have a mass of 400 grams. The blocks are fixed to the horizontal rods and the initial velocity along the circular path is 2 meters per second. So this is 2 meters per second as shown. If a couple moment m equals 6.6 Newton meters is applied about CD of the frame, determine the speed of the block when time t is 3 seconds. The mass of the frame is negligible, it's free to rotate about CD. Okay, so when you see this problem, you see things spinning in circles. When you see things spinning and there are moments, the best bet is to think about applying angular moment and impulse. Okay, so in this case, there are two options: conservation of angular momentum or principle of angular impulse and momentum. Which would you apply? Principle, right? Because there is an external moment. Okay, and it is not internal, it is external. So it says that HO1 plus integral MO dt equals HO2. Okay, I'm going to skip the vectors, and it's only because, again, in the previous problem, H is, or M is about the, let's call this z-axis, it's about the z-axis. H is about the z-axis because H is R cross MV. The vector V is in the plane, in the, if you like, Z. V is in this way, R is this way, right? Okay. I should maybe try it here. V is this way, R is this way. So when you do R cross V, you get a vector which points in the Z direction. This is along Z. Okay. It's very unlikely that you'll have a problem in the book or in the exam which will be two-dimensional, three-dimensional H. H will always usually be in one direction. It will be along Z, where Z, not Z, but one axis, not about two axes. Okay. So HO is the angular moment, it's the angular momentum of A and B, and since they are two of them, I will say 2 times R cross MV. I'll write it as MVR. Okay, let's call that V1 because it's going to have a certain initial velocity. Plus integral 0.6 dt, because the moment is 0.6, from 0 all the way to 3 seconds equals 2 times mv2r. Right? Now, what we do know is the mass is 400 grams, so it's 0.4 kilograms. The initial velocity is it given? 2 meters per second, right here. 2 meters per second plus 0.6 dt. That's going to be simply 0.6 times 3, right? I forgot R. Okay, my bad. R is 0.3 plus 0.6 times 3 minus 0 equals 2 times mass is 0.4 kilograms times the velocity, which is an unknown, times R. Okay, so only unknown there is V2, and V2, after doing the math, comes out to be 9.5 meters per second. Okay, is that clear? This is a straightforward problem. Okay, last question, then I'll let you go. So if the rod of negligible mass, this is the rod of negligible mass, is subjected to a couple moment of 30t square Newton meters, and the engine of the car supplies a traction force F equals 15t newtons to the wheels, where t is in seconds. Determine the speed of the car at the instant t is 5 seconds. The car starts from rest. The total mass of the car and the rider is 150 kilograms. Okay, so the rider is at rest, and then it will be m equals whatever formula given there is applied, and also is the force F acting on the system, because of which clearly this rider is going to speed up. You've got to find the speed of the rider after a certain time. I think it's 5 seconds. Okay, so things are going in circles, so clearly you've got to use either conservation or principle of angular impulsion moment. Which would you apply? Principle, because there's an external moment, it's not internal. So the same thing, principle of angular impulse and moment. Okay, which says that HO1 plus MO dt equals HO2. Okay, again the H is going to be along this axis. That's why I'm writing it as a scalar. So the initial angular momentum is 0 because the rider starts from rest. Now MO is 30t square dt. Time goes from 0 to 5 seconds, but then there's also an external force due to the moment due to the force, right? That's 15t. Okay, but we need to convert 15t, which is a force, into a couple or a moment. And the way we do it is we multiply that with the moment arm, which is in this case 4 meters. So here you got to be, well, a little bit careful. This moment is acting in the z direction. The way to find the direction of moment is you curl your fingers along the direction of m, and your thumb gives you the direction of movement. So in this case, it's around z. The way I've shown it's positive. If you find the moment due to the 15t force, so 15t times 4 meters, right? 0 to 5 dt. Again, the question is, what is the sign? So 15t times r. R is this 4 meters. So the moment about point about z-axis, the way I've shown it, is going to be in the counterclockwise direction when seen from top, or in other words, it's going to be the same direction as z. So it's going to be positive. Okay. Now, if I had changed this into a force which was opposing motion, it was friction force, for example, and friction force would have been in the direction exactly opposite to that force, in which case the moment would be in the negative direction. So you have to put a negative there. So changing that sign is going to be very important. So that's why you got to think about a coordinate axis before you solve this problem. Otherwise you can mess up the sign, which will mess up your answers. Okay, so this is equal to m times, so mass is 150 kgs, the velocity is unknown, and the radius is 4. Okay, I would like you to fill the dots. There is a bunch of steps you need to do. You need to integrate the equations. So try to solve this yourself. It will be good practice. And check if you get v equals 3 point, so v2 3.33 meters per second. Okay, I'll see you on Wednesday. I'm done with chapter 15. All we got to do is chapter 19, and I think I should be done hopefully next Monday, which will give us 2 days to do the